You guys know I asked for Office, the classroom support last time. They couldn't install the software anyway, so we still have to improvise. Okay, but I'll try my best to videotape this whole things. And I also put the lecture notes on the simple regressions. I cover simple regression in almost every class at the very beginning, experimental design, Bayesian class, because I think it's fundamental. So you should know how to use it. And but for some of you already in my other class before, here's the experiment or the homework you have to do, okay? And the homework is like this. Oh, here we go. So you create a segment, okay? You want to do it horizontal, you want to do it vertical, I don't care, okay? And this is your baseline. Put the baseline as high as possible, okay? And then ask your girlfriend, boyfriend, anybody, your classmate, be your subject. Start very, very short, okay? And then you just, say, close your eyes, increase a little bit, okay? And sometimes you can fake it. You don't touch it. You just pretend you did. And ask your friend says that, of course, don't show the calibration. Just show the display, right? Like a PowerPoint presentation and said, is it longer or the same? And then they'll say, it's the same or longer. Until several times they said, yeah, I know this one is a little longer. And then you say, okay, now we measure the differences. And then now you use the new one as the baseline. Of course, if you get closer, you can tell it's different. And now the new one, the top one is the new baseline. And start increasing a little bit until he said, yeah, I can tell the difference, okay? And if you guys don't like this simple PowerPoint experiment, another thing you can do, use dog food, or you have grain of sand or anything at home, and have say 2 tubes of grain, cereal or whatever, and then start from nothing, and increase a little bit, and say, oh, can you tell the difference? No, yes, confirm. Okay, then move down to the next one. You guys follow me? So if you do that long enough, and sooner or later, you will have a data set. The data set will look like the data points, the assignment I give you in your homework, okay? And I'm gonna show, okay, let me show that first. Okay, the data point should look like this. Start from a baseline, okay? Start from a baseline. This is a phi. And then, until confirm, it's 33.99. And it's 37.8. Just increase, decrease until it's confirmed. So now you just have a series of increment, okay? And for the homework's sake, just have 10 trials. 10 confirmation of numbers. So far, so good? Increase until you say there. And, if you want to play with lighting, if you have a toggle switch at home, you can say, okay, increase a little bit until you feel the differences. Okay, and if you really want to torture yourself, turn the heaters on, or air conditions, is it colder, is it hotter, until you can tell the difference. But basically, there's a physical something you need to judge. Is there an increment or not increment? So far, so good? Okay, so after that, we will use the differences between upstairs and downstairs. And of course, Weber's law just says that, so on average, what's the difference between the two? So you just basically do this, right? Okay, I'll do it. Okay, so using the differences over the baseline and take the average. On average, I can tell about 12% of differences. That's my human psychophysical resolutions, okay? But like I said, Webers did this 100 years ago, and he realized that there's an internal noise. When we see things, when we hear things, there's an A term. You need to get involved. So we need to use regression, okay? And to get a regressions, last time I already showed you, all you need to do is figure out the slope, okay? No, let's do it the Excel way. Find a slope between phi and delta phi. Find an intercept between phi and delta phi. Okay, and then your internal noise will equal to the slope. No, I mean the intercept divided by the slope. So now whatever you do, you will have the answer by just plug into this black box. You have the answer. So far, so good. But of course, you know, I don't want you to do it this way. And the other thing is that I don't want to give you my Excel. For some of the students, they have the Excel more than once in my other classes, especially in the last 2 years because of COVID. A lot of times they just say, oh, give me your Excel, give me your Excel. I did. And they promise, okay, they will do it by themselves. Just double check the answer at the end. But when they turn in their homework, how many times I realize they never done it themselves. They just plug and play my Excel. Quite a few people done that. And why I'm upset, because there's a certain meanings for system engineering to realize what's the world, how we turn the world into a set of mathematics in order to model or calibrate or to, get things done. The minute you start plug and play, well, you can plug and play now. How many of you can memorize every column and says that, oh, I can do it anytime? Some of you will say, I'll check on your note and your videotape when I need it. And guess what happened when they in their senior projects? Hey, Simon, you remember you showed us that regression? Can you teach me to do it, redo it again? And I feel like this is like bicycle riding. Learn it now. And I promise you, I'm 60-something. I've been using this stupid things for the last 30, 40 years, again and again. So it's not like something only good for the classroom. It's really useful. Okay, so gentlemen agreement, please visualize it, okay? Now, how to do that? Let's first let me show you the PowerPoint, I know I have my, right here. Okay, so we start from a simple regression. There's a regression line called Y. The intercept is B. The slope is A. And then, of course, since this is not a perfect line, there are error terms. Up and down, up and down. So imagine this. You have 10 observations, so I equal to 1 to n equal to 10. Every time you have a y, you plug in the a term and the b term, you have an error term. And at the end, if you have a perfect line, the error term for arrow 1, arrow 2 to arrow 10 square that thing should be as small as possible. Agree? So that will be the summation of every possible observation you have, y1 minus b. Oh, I have a mistake here. Here should be minus a term, or I have this whole thing, both should be negative, right? Epsilon equal to y minus b and a. Okay, and if this square term is very, very small, then the partial derivative of this error function or this loss function L, partial derivative of a should equal to 0, partial derivative b should equal to 0, and if you take the second derivative, partial L square, partial a square should be greater than 0 because we're looking for the minimum. And the other way you can think about it, why you're looking for the minimum. Sum of square, a bunch of square term, what will be the smallest number you can get? What is the smallest number you can get when you sum a bunch of square term together? Victoria, you're okay. So, what will be the smallest term for all the error square? Smallest you can get. 1? No. Nada. 0. Right? Can you have a sum of square is negative? No. So you basically said that, okay, error this way, error that way, and so the second derivative should be all greater than 0. But we don't care about the second derivative. We only care about where's a and where's b. So we need to find the L and b by taking the partial derivative. Partial L, partial a equal to 0. Partial L, partial b equal to 0. So once you do that, you know that a bunch of summation y stay there. B term, you done it for n times, so it's mb. A terms, you done it for summation x, so it's summation x. So first derivative end up with summation y equals nab, this equal to this. And then second one is the b term. The b term actually is related to the interaction, the change between the two. Okay? Now, how to visualize this? Let me do it this way. You guys see the screen? No? Oh, there we go. Okay. Here are 10 observations. Up and down, up and down. Okay? Now, if I'm only changing the slope could be here, could be here, could be here, could be anywhere, right? But I know that when I'm moving the slope too far down, or I don't like this one. Yeah, I'll do it this way. When I move the slope too far down, all the error term will be what? Positive error, positive error, positive error, positive error. There's no negative error to balance it out. But if I move this slope too far up, it's all negative error, negative error. So whatever I do, when I move the a term, I need to move the slope. I need to move the slope such a way that half of them a little above, half of them a little below, but kind of like it's kind of like a tug of war between above and below until they balance. Agree? That will make the slope very, very small. Some second things, if I have an intercept, okay, intercept down below here, nonsense, because everybody's way above. Intercept up here, nonsense. So there is a way you can move the error term somewhere in between to make the whole things as small as possible. So that's the way to visualize, okay, these two equations. And when you try to visualize these equations, okay, find the b term and find the a term. Here is a cheat sheet to remember that, okay? See here? First time, all the y get sum. B got summed 10 times because B is a constant, so it's MB. AX got summed 10 times, A is constant, so A summation X. Follow that? So these things, just put a summation in front of every term. Summation Y, MB, A summation X. Can you see that? Next time you say that, but this is really about the interactions. So it's everything times X. So Y hat times X become summation YX or XY. B, everybody got the contribution of X, so summation X. And AX, you already have X once, so X again becomes summation X squared. So now you turn this into this two simultaneous equation based on the least square optimization. And least square optimization basically said that I need to manipulate the slope, I need to manipulate the intercept, such a way that these things will be as small as possible. So far, so good? Finally, how to solve the simultaneous equations. This is your high school or junior high algebra. First, you figure out the determinant. So the determinant is basically the things on the right. And B, summation X, okay, B and A, you cannot see it because that's the term you need to solve. So the denominator is always N summation X, summation X, summation X squared. So look at the denominator is nx squared times summation X squared, okay? And what does that mean? Let me get back here. Okay, summation X squared minus summation X squared, okay? And then if you take the n, both sides have the n out, okay? Take the n times, what does that mean? That's the variance, right? How I vary by myself. So look at here. The denominator is about Houston. What happened here again? What's this? Click. Click where? Click here? Oh, okay. Oh. Okay, so A term and B term, now you have the same denominator. The denominator is how X vary by itself. And on top of that, you have two different types of replacement. So you can, if I copy the matrix, the determinant for the denominator and put it upstairs as the numerator, then, you know, same thing divided by same thing, B equal to 1, A equal to 1, right? Divided by itself. But obviously, I'm not dividing by itself. I'm dividing by the change. So the change here, first time, for the B term, you just keep the summation X and summation X squared, like the stuff downstairs. But then plug in the left side, summation Y and summation YX. So now summation YX, is the numerator. And now that basically says that, oh, in order to make my B changed, okay, if my B part for my denominator equal to all the change I have for summation Y and summation YX, that will be my B term. However, if I said that, oh, I don't want to change my B part, I want to change my A part, so A part is substitute. Rather than using summation X squared, I'm using summation YX. Now the numerator becomes the denominator, but on the right-hand column using summation YX. If you do that, you will get your A term. Okay? So first thing first is how did you find this? we will talk about the matrix form when you guys take my DOE. DOE is mandatory for your later time. We'll do the pure matrix X transpose X, X transpose Y fashion. But here, I'll give you 30 seconds to see, to let you ask questions. Can you visualize this? First thing first, there's a regression line. So you have an intercept can be changed and a slope can be changed. First line, question, no questions. Second line, if there is a differences, the total differences, summation error square equal to L. L really is the differences between the Y observation and your prediction B and A. And then summation this whole things together. That's your second term. Question, no questions. If you feel you want to sleep, stand up for a second so you can keep yourself awake. Okay, so second term, no problem. Yes, our problem, no problem. Now, if you have this sum of square, loss function need to be solved. And you said that I need to find a good A term and B term to make this as small as possible. The smallest I can get is 0. So you take the derivative, first derivative equal to 0 will be where is your optimum. Partial L, partial A, partial L, partial B, both equal to 0. That will end up with this two simultaneous equation. To solve those two simultaneous equation, you must done this when you in junior high, right? Y equal to 3x plus something, y1, y2, and then try to find where's the two line cross. That's exactly what we're doing here. Summation y is a number. B and A need to be solved. Summation yx is another number. B and A need to be solved. Okay? But solve this simultaneous equation, you can use determinant method. Using the determinant, so this two simultaneous equation, no problem, right? Turn this two simultaneous equation into the determinant part from the left side, and then the numerator part by using the same denominator part by substituting B using the right-hand side, A using the left-hand side, and then you can solve the A and B. So far, so good? Young man in the back, fully visualize? Okay, now let me do the Excel way. Okay? Okay, the Excel basically said that I need to find a delta phi, okay, as a function. Delta phi is a function of phi. So delta phi is my y term, and phi is my x term, okay? So in order to do that, look at the equations. I need a summation xy. I need a summation x squared. Yeah. I need a summation x squared. Okay? So now, how to solve that? First, find the denominator. Denominator equal to summation x okay, summation x minus n summation x squared. Okay, pop quiz, young man in the back. I have 10 observations, why n equal to 9? No. Uh-huh.
Because you only have 9 values after
How many differences do I have?
9.
Yeah, so 10 observation, you can only do 9 differences. So with 9 differences, you can only have n equal to 9. Okay, that's how you end up with your denominator equal to summation x C14 square minus n times summation x square. Okay? So first, the denominator problem, no problem. You can get a denominator, right?
Yeah.
Okay, next. Once you find a denominator, you need to find a slope. The slope is something minus the denominator, and something is substitute the right hand, the equation on the left hand side on your notes. I upload the notes to your class notes, so you should have it. Okay, so you have that PDF file, but yeah.
Where did you say they were? Because I was on the games page looking.
Okay, go to assignment 7.
Is it lecture 7 or an assignment?
No, homework 7 today.
Okay.
Because the lecture, I'm using the lecture note last time. Found it?
I see assignment 7. Okay.
There's a PDF file appended. Got it? Okay.
Thank you.
Uh-huh. Okay, well, I hate to be like an old clock. Please don't just copy paste. Try to visualize it. The more you visualize this, the better you can use it later. Okay, so now the numerator, first time we substitute summation xy and summation y to our denominator part. So now you divide that, you get your slope, okay? And your slope is 0.1084. And look at what Excel tells us directly is 0.1084. Got it? Okay? And then you get your intercept, okay? But now, here's the tricky part. Remember I told you guys the Weber's Weber did not use delta phi over phi later on. Somebody said that, well, every time we see that tiny error at the very, very beginning, so you need to add that internal noise term. That internal noise is the baseline, okay? And a lot of time we said that we would like to have the Weber constant, K, as sensitive as possible. Means that I have a small k, just tiny bit of differences. I can tell that you're good or you're bad. So k small is sensitive. Agree? A small means what? You don't have too much internal noise to start with. If you have too much internal noise, means what? Well, you're very, very good in large scale. But the minute we move to the small scale, you start making mistakes. So this whole thing's, okay? A need to be small, K need to be small. So delta phi regression equal to K phi plus AK. So K is your slope, AK is your intercept. So intercept divided by intercept divided by intercept divided by your slope, okay? You get your internal noise, okay? So your homework is observe 10 observation, incremental, weight, light, length, I don't care. Any physics transformation into psychophysics. Yeah?
So we don't use the data that's in assignment 7?
Well, you can use that to double check, make sure that, since we're gonna upload this part of the homework video for you. So you can double check, make sure your homework's correct. You have the right Excel file to use.
Yes.
Yeah, but I don't want you just plug and play with my number. Okay? That make sense?
Yeah.
Okay. Okay, so now let's move down to new stuff, okay? Yeah,
Can you make that clear on the assignment 7 posting, like what it is we're doing?
okay. Is TA here? Okay, can you just write it down one more time? Everybody design a psychophysical experiment with some stimulus with increment for 10 observation. And then, I don't care its length, weight, whatever, you have the physics. Turn them into two part, internal noise and sensitivity, Weber constant. Make sense?
Yep.
Okay. Okay, let's keep going. How come PowerPoint's Google Chrome is not on?
Might just be loading.
Like me, aging process. Hey. Okay, here we go. Okay, the everything's I recorded, I'll upload it, but it's not part of the original lecture notes. This is, because the computer not working, and per Victoria's request last time. Okay, let me see. Where am I? There we go. Oh, I already loaded last time. Okay, and then after Weber's successfully defined this stuff for probably 30 years. There's another German's coming out. His name is Fechner. Fechner says that, well, why we use, the hyperbolics? Why can't we just use log? And what did I say about log? What is the benefit of using log? I mentioned that last time. Young lady, what is so good about using log? Log can solve 3 different type of problems. What are the 3 problems? I don't want you to see your notes. I'll see if you can speculate it.
Log can kind of go in different.
First things is whenever the phenomenon is what? Exponentially grow, you can bend it into a straight line. And what's the second one? Second one is when the scale increase with your magnitude. So the variations proportional to the magnitude, it becomes a trumpet shape of your data set. And when you take the log, you compress that trumpet shape into constant error term. So we can abuse regression. What's the third one? Third one is the most important one, relate to human factor. Anybody remember? What's the third one? Got something to do with the derivative. Anybody? I mentioned that last time. The log something, okay? The log something, the derivative of this equal to what? What's log function derivative? Equal to 1 over the magnitude, right? So, if I write this in the d phi cube form, d log phi becomes d phi over phi. And if in a Excel or operational system engineering format, is the finite differences of the differences over the magnitude. Okay? So you can use this 3 different methods, back and forth, to resolve a lot of data mining, machine learning's problem. Because in data mining, machine learning, the Google driving car, okay, what is the Google driving car trying to do? Oh, is this, good enough to pass? Not based on how the electronic feel, also sometimes based on how people feel about it. They feel comfortable or not comfortable with it? And if you want to do that, you're not asking the machine's measurement. You start asking how human feel. Can you feel the differences or not feeling the differences? So there's a magic term you need to know. Okay? The magic term is this. It's called JND. Okay?
Still loading.
JND copy paste. If you go for say Microsoft or Google for jobs, JNT stands for just noticeable differences. Just noticeable differences means that how much can people tell the differences? And think about it. What kind of experiment I just asked you to run by yourself? How much extra can you tell the differences? Every time you only try to figure out, oh, what is the human skill, human resolutions, okay? So is it possible that I design something so detailed, you think it's wonderful, but people don't give a, yada, yada, they don't care. Why? Because they cannot tell the differences, okay? On the other hand, the road is, for example, all the highway, shoulder, they have undulated pavement, right? Why they need to put undulated pavement? So if you are swirling, it will give you warning, right? If the undulation is too small, do you think people can tell the differences and say, oh, I need to wake up, I'm getting too close to the shoulder? So you need to make the undulation just enough. And how to figure out what is enough? Just noticeable differences, okay? And how to solve the just noticeable differences? What you do, rather than, okay? Rather than in the Weber's law format, you just do this, okay? In Weber's law is what? 10 is the baseline, 12, 14, every time find a delta, and then delta phi over phi, right? JND, you don't need to do that. You don't find the differences. All you need to do is this. Take the log of your stimulus. Take the log of your stimulus. Once you take the log of your stimulus, and then all you need to do just using the total level, okay? and then using log phi psych, the total level, divided by, so 1 over c is this, using log phi and psych. Here's psych, just noticeable difference. Here's log, okay? And then use this divided by this. You will find a k-term, and then take the average of your k-term. And the average of your k-term is your Fechner's differences, okay? So for your homework, once you find your Weber constant, find your Fechner's constant k, okay? Easy, right? Let's just take log. Oh, by the way, it's taking natural log, okay? In Taguchi, for experimental design, we're using log 10. That's because Taguchi, when he developed his measurement, he is an electronic engineer for the previous, for the Sony or National Electronics in Japan. So he using decibel, so he used log 10. And for psychophysics, we don't use log 10 base, we use natural log base. Okay? Now, something for fun. Okay? People using the terms to evaluate all kinds of physics and the sensations, visions, auditions, cutaneous, as what they call proprioceptions, and proprioceptions including pressure, temperature, and then vibrations, and body motions. Okay. Now let's talk about eyesight for visions. Okay. Oh, before I finish that, we done substance 4 last time, right? Do you think where you mentioned control balance? So where the sensation of balance coming from? How you sense where is your center of mass? Are you balanced or not balanced? Okay. The first thing is that you have 3 semicircles inside your ears. It's vestibular system. The semicircle is a tube in XYZ 3 dimensions. And inside the tube, there are hairs and then some liquid. So when the liquid slush the hair, you get a sensation of forward, backward. Okay? And most of the astronauts, once they stay in a space station for too long, that vestibular system is not well calibrated. And if it's not well calibrated, once they landed after a shuttle flight, they cannot make a sharp turn. The minute they make a sharp turn, they'll fall. So they usually, when they're coming down, people guard them because they cannot maintain balance. So first thing first is vestibular system. And the other thing is used inside your body, all the muscle got a tendon called Golgi tendon. The tendon provide the tensions for your front and back. So you use that hamstring, gastroc to maintain balance. And then the third level actually is from your skin. And you can sense the differences. Okay? That's how you maintain balance. Another thing you can use to maintain balance is using your eyes. Okay? And using your eyes, inside our eyes, we have 2 different types of camera. The color camera is the very expensive camera. It's called cones. Okay? We have some very, very nice color camera. There are 6 or 7 million of them. But then we have some cheap camera. We have 130 million of them. They are black and white shade, and we have 130 million of them. Okay? And the distribution of the beautiful camera is usually at the center. Look at the color picture of your loved one. And the peripheral visions, we use the cheap camera. And if I've been to Fort Benning, watch how they train the special force, okay? When they patrol at nighttime, okay? And you've probably seen it in the Vietnam Wars movie, in the jungle. Usually they carry the rifle bent forward. Do they walk straight or they walk swaying their head? Why they move their head? Anybody?
To change the focal point.
To change your focal point so you can take advantage of your good camera or bad camera. The bad camera. Because the bad camera, since there are not much information, but it can sense the motion really, really quick. So we're really trying to figure out is there a big bad wolf following? So you use your peripheral vision for that. Okay? The good visions need long time to calibrate. It's not very good to detect things quick. You follow me? The cheap camera can help you detect things really quick, but the bad camera the good camera help you to see something deep. Okay? And so we use the visions for that purpose. And we can calibrate the visions using another approach that's called optic flow. Okay? And now I'm trying to relay this to the NASA study and how we use the optic flow. Okay? How many of you ever seen the 3D movies in a mall? The simulator? Ever sit in a simulator? They sometimes tilt a little bit, let you use the gravity to feel like you're accelerating or decelerating, because that's trying to fool your semicircle vestibular system and your skin and your tendon. The other thing they try to fool you is using the optic flow. Basically, they have the image like this. It's like the snow image. Usually they have a screen, okay? And they can move the center of focus up and down, left and right, to make you feel you're moving left and right. But at the same time, they have this kind of snowstorm floating out. That will give you the sensation of the speed, okay? And what is important these days is that a lot of time we have backup camera for Google self-driving car. And what's the most challenging thing is that humans sometimes can use very, very little optic flow to figure out, oh, there's a little boy behind us. Much, much better than your self-driving car camera system. So the self-driving car, they use another one to help. It's called LiDAR, LiDAR system. And we have a couple next door. Dr. Lei is using them. Okay. Okay. Yeah, this is for up and down. Next, let's move down to power law. And everything I talk about is around 19th century industrial revolutions. And then in both Fechner and where's the down, what?
That's the arrows on that side, the full screen. No.
Where?
Next to the zoom button. You want full screen or do you want it down?
No, I just, oh, right here. I got it.
You can just plug it in.
Okay. Okay, so everything I talk about before developed by the German mainly before World War I. Okay, and then psychophysics become hot again after World War II. Why? Because during the Cold War, what happened? Space race, and also we get into the jet age, and a lot of things were flying, driving, and the sensation is not just about one thing at a time. It's the combination of several things. So this guy is called J.J. Stephen, and Stephen, actually, if you look at the literature, there are two Stephen. One Stephen, the other Stephen, I can't remember, is his wife. Okay, and both of them work in the Air Force Base. You guys can guess where is that Air Force Base? Most of the Air Force research done.
Virginia,
Okay,
Maryland.
Wright brothers test their flights in Carolina Beach, right? But where Wright brothers originally from? Ohio. So in Ohio, there is a very, very large Air Force base. What's the name of that Air Force base? Wright-Patterson. Okay? So Wright-Patterson, they sponsor a lot of research on psychophysics. Okay? And when I was grad student, my advisor got a lot of projects because the PhD student of his was the director at Wright-Patterson for human factor research at the time, Joe McDaniel. So I had a chance to see a lot of stuff done over there. And what's the best things about Air Force or in the military? You get a lot of soldiers, very, very healthy. You ask them to try this, try that. And this, of course, in the old days, the informed consent is, well, especially military, they want to figure out the limit. What kind of limits they try to figure out? Put them in an environmental chamber. Extremely hot, extremely cold, extremely humid, extremely something, and see what's their capacity. Okay? Do you think that's important to figure out humans' capacity? Is that important besides military application? Yeah? People say it's not. Why? Because they said that today all the foundry or aluminum or steel mill, you use robot. But that's not true. If you go to Ohio, go to the Rusty Bell, Pennsylvania, all the way to Chicago, you still see a lot of humans in the very, very heavy protective gear to deal with the extreme conditions. Okay, so there's still some industry require human operation, and the other thing is that even you use robot, okay, to deal with a lot of extreme environment. Do you think human can stay out of it forever? When the robot is out, who are you gonna send in? Human. Okay. So psychophysics now getting into the other domain. And before I talk about other domain, here are the things for those of you never be in my class before. Human measurement or measurement theory. There are 4 different types of scale. Please memorize it, because if you can find another scale outside this range, okay, you get Nobel Prize. Okay? 4 different scales. The first scale is called nominal scale. Nominal scale means that you name it. You can tell the difference. So color, black, white, green, red is a label. So if I say I have a racehorse number 25, that 25 got nothing to do with big or small. It's just a label of that horse, 25. So that's a nominal scale. Second, ordinal scale. The ordinal scale talk about rank. Okay, rank means that I'm better than you, you better than me. The preference, I like this better than that. Okay, the only thing is that rank scale doesn't tell you the distance. So here, I'm closer to the board than Howard. Agree? I'm closer to the board than Howard. I'm only 1 inch away. Howard is 10 feet away. I'm closer than him to the board. I'm 9 feet, 10 inches away from the board. He's 10 feet away from the board. I'm still closer to the board. But ordinal scale, you don't care about the distance. All you care about is the rank. And why this is important? The Winter Olympic just finished, right? For the figure skating, you be the champion. All you care is that you're better than everybody else. Do you really care how much better? Okay. Yeah. So same things for quality control, for design, a lot of time for competitions. All you care about is what? I'm a little more reliable than my enemy. But how much better? As long as just noticeable. If your customer can tell the differences, small or big, doesn't matter. And sometimes they even talk about a lot of consumer products. Do they say, I can beat you by 3 different levels? Do you think when I promote my products, I will give my products the best out in 1 shot? You guys follow my questions? You design a product, I design products. I'm 3 versions ahead of you. So when I try to promote my new products, I should use the best out in the market.
Oh, no,
Why not?
because then you have nothing to go off from.
Yeah. So I will promote one, iPhone 8, better than Samsung, even though I have iPhone 9, iPhone 10 already in my pocket. But I won't push that up. Next year, you try to catch me, I promote another one. So I'm always saturate the market with something a little better than you, just noticeable. Because if I'm ahead of the curve too much, there's another thing. So consumer, a lot of times they need time to learn the new products. I admit, my son helped me set up the phone. So far, there's still a lot of function. I have no clue how to use it. Okay? And it takes time. So to be better, people sometimes say, ordinal scale is stupid. Just rank. And for me, in system engineering, if you can rank it, it's good. Okay? Next, interval scale. Interval scale is based on distance. All the experimental design, all the Bayesian class, most of your statistics class, most of your optimization class is based on interval scale. And interval scale, why is it good? Because interval scale, you can do partial L, partial A, partial L, partial B. If you have interval scale, put that down, you can have gradient. You have gradient, you can have optimization done. Okay? So you can find the differences for slope. Finally, ratio scale. What's ratio scale? Ratio scale is percentage. And in order to have percentage, put that down. You cannot have percentage unless you know what is absolute zero. Okay? Have you ever seen absolute zero in your life? Yeah? So anybody remember what's Kelvin?
That's the absolute zero is like the coldest theoretical temperature.
And theoretical temperature, negative 273 degrees Celsius. What's so special about that temperature?
There's no possible motion.
And why there's no possible motion?
Speed of like the subatomic level is so slow.
It's so based on the slope, at that level, there is no energy. There's no energy, there's no vibration, there's no vibration, there's no temperature oscillation can be detected. Okay? And in psychophysics, we will use ratio scale because we will have a theoretical zero. And how to figure that out, we will use the log function. Okay? Now, because I need to let you go, so first I'll just say that power law basically says that psych equal to kb rather than the log function. Now I have a power function. The A term, or alpha term here, could be greater than 1, could be equal to 1, could be less than 1. Okay? And when you have something greater than 1, means that you exaggerate. When you have something equal to 1, that means your psychophysics and your physics are proportional. And if your alpha term equal less than 1 means that you taper out. Whatever you feel after you've been in that room too long, you cannot tell the differences. And one thing is very obvious, when people in a very stinky environment, okay, usually say international flight, okay, sometimes you feel they spread a perosa to clear the air, especially these days they use a lot for COVID reason. But once you get into that, 777, you smell something funny at the beginning. But within probably 40 minutes, you don't smell any things anymore. You get used to it. Okay? Some things, when you go to a movie theater, when they turn, the lights off at the very beginning, you need to turn your head around to use your peripheral vision to get a sensation of where you are. But after a few minutes, you adapt to it. So we're looking for A term. A lot of time, if A term, put that down, A term, this alpha term is greater than 1. The bigger the better is for warning. Equal to 1 for calibration. Less than 1 for adaptation. Okay, so let's find a few terms. J.J. Stephen did it in Wright-Patterson. Okay, first look at the number. You guys have the notes. Okay, some number, loudness. Okay, if you're in a very, very loud environment, disco club, after a while, you get used to it. Okay, you're in a very, very loud working conditions, after a while, you have hearing loss, but you get used to it. Okay? Projection lines and taste, saltiness, okay? Exaggerations or adaptation? Exaggerations, okay? If you have something too salty, you feel saltier than what's really in there. Okay? Everybody look at this. Did you see anything that, holy cow, that is really, really a large exaggeration? See that? Which one is a lot of exaggeration? Electric shock. Yeah. So if you want to give people warning, zap them. Of course, don't kill them. Just give it. PTOT, they zap people. I think it's less than 12 volt. Okay, but it's good enough to give you that sensation. How many of you ever played with a 9 volt battery? If you just taste it, the positive and negative, you get the tiny 9 volt battery sting, and you can. So you did it? Okay, we're same country. Yeah. Okay, and squeeze rubber, that's the one that give you the wrong, your taper off. So people talk about, your Nike shoes, walking shoes, very, very good, very, very comfortable. Very, very comfortable when you first get it. If you got your Nike more than 2 months, you don't feel as comfortable as before. Okay? So some things, if you work in the industry, your workers say, hey, we want those fatigue-reducing mat. Guess what will happen? When you first spend $200, buy the mat for everybody says, oh, this is wonderful. I can tell the difference. Ask them 3 weeks later. Nobody can tell the difference. Okay? So one thing people talk about is if there's adaptation and you want them to feel good, let them use it for a while, take it away, and then put it back. And they will, appreciate it again. Okay?
The smell score.
Huh?
What was the score for smell? We were talking about that. Oh, very low. That makes sense.
Yeah. We can test that very quickly. Okay. Sugar and taste. Okay. Our tongue. Where our tongue got different zone to taste different things, right? To taste the bitterness is in the root. Okay. So a lot of time people will say what? When you swallow the pill, have some water in your mouth, and then gobble in as quick as possible. The worst thing to have is let the kids hold it in the mouth. The longer, the closer to the root of your tongue. Okay? But generally speaking, okay, for warning sign, you use higher than 1 value. For adaptation, you use less than 1 value. For calibration, for transfer function, you use equal to 1 value. Okay? Like warning signal. Okay? Female warning signal versus male warning signal. Voice. Which one provide better alert effect? Female. And actually even better is children's voice. They did a pilot test before on the Navy pilot. Okay? The warning is, Daddy, the enemy missile is locked on you. And when you use the kid's voice, the reaction time is the fastest. Okay. And next, so the transfer function above 1, less than 1, equal to 1. So you can tell if it's above 1, when you take the log, that parameter become linearized. Okay? So what is the best use about that law is using that for simulator study, like try to develop flying simulator for drone. Okay? And the way how you did it is the following format. First, you have 2 psychophysical power law expressions. J for physics 1, power was A, and the physics 2 is constant K and then B. Okay, so now I have 2 psychophysics. Say I've tried to let you using the optic flow or using the tilt of the gravity to judge your speed. So this is sensation 1, this is sensation 2, and then I want you to use one sensation to calibrate the other sensation. That's why it's called cross modality. Once you take the log on both sides, you can bring the exponent A and B down. So now become log J, A log phi 1, log this. And finally, you can move the parameter to the other side. So now you basically can figure out that how much log sensation of phi 2 can generate the sensation of phi 1. This is how they develop flying simulator, driving simulator. Okay? Usually, because flying simulator, driving simulator, you're not flying it. You're flying a fake one. Oh, those drone, Air Force and Army fly. A lot of time, their home base is in Las Vegas, but the airplane, where is the drone? Could be the other side of the Earth. So the flying is through satellite control. What will be the problem? Do you think when pilot flying a drone, they don't get motion sickness, or they will get motion sickness. Why they get motion sickness if they sit still?
The motion that you're seeing.
The optic flow. Okay? So I don't think that our department got this tradition work for military, but cross modality is a big topics in all kinds of motion sickness and flying simulator studies. Okay, so this is psychophysics. Okay, now let me move to the next topics. How much time do I have?
2 minutes.
Okay, so next time I'm going to talk about signal detection theory for homeland security, to detect a bomb, to detect bad quality products, and it's a big homework. The homework relate to data mining in what they call discriminant analysis, the same statistics, okay? But the foundation is in psychophysics. And your homework, Weber's law, Fechner's law, they developed 10 data by themselves. I want to find the Weber's law 10 data points, the Weber's constant and internal noise, and Fechner's law a constant. Okay? See you next time.